Hello everyone. In this video we are going to discuss about hashing. So hashing is one of the most important topics from data structure. It is very important in Gate also. We do have many applications of hashing which we will see in our subsequent videos. Before going to the actual definition of hashing, let's try to understand why hashing is needed. We have already studied about linear search algorithm. So linear search algorithm is an algorithm in which the search time complexity goes with order of n. In linear search algorithm, the elements may not be in the sorted order, and the element which we want to search has to be compared with each and every element present in the list. So if there are n elements, then the time complexity of searching for a linear search goes with order of n. Next we have binary search. In binary search, the elements of the list need to be sorted, and the element which we are going to search, that is also called key, has to be compared with the mid element, and if the element which we are going to search is smaller than the mid element, then we search to the left of the list or we search to the right. So in this fashion, the size of the list goes on decreasing by half at every iteration, and it results in a search time complexity of order of log n. But the constraint is the list has to be sorted. Next, we do have other searching algorithms also, as for example in a binary search tree. This is a very special case of a binary tree. The complexity of searching a key in a binary search tree will go to order of log n. But in a worst case, it can go to order of n also when the tree is skewed. So better, it is not always guaranteed in case of binary search tree that the complexity is going to be order of log n. But in worst case, it can go with order of n also. So to guarantee a search of order of log n, we further improvise this binary search tree with AVL tree. But then we have a question in our mind that can we still improve our search algorithm? Means we started from order of n from linear search and we reached to order of log n, that is guaranteed order of log n in case of AVL tree. Now we try to further improvise this algorithm, search algorithm, in terms of time complexity. Whether we can improvise or not, we will understand it through an example. So let's try to understand the concept of improving the time complexity through an example. Suppose we are having some elements as 8, 3, 13, 6, 4, 10. And we want to search an element. What we are doing, we are taking an array, and the element which we want to search, we are storing that element at its own index. As for example, suppose element 8 is stored at the index value 8. Element 8 is stored at the index value 8. Element 3 is stored at the index value 3. Similarly, element 13 is there, which is stored at index value 13, as we can see here. Suppose the key which we want to search in this array is 10. Whether 10 is present in this list or not. So since we have stored all the elements at its index location only, so directly to search 10, we will search the index 10. So if we search the element 10 at index 10, yeah, we have found it. Similarly, if we want to search an element 12, so we will search the index 12. So element is not present. What does it mean? It refers to the fact that at one go, without iterating the total list, we can search an element in the list in a constant time in order of 1. So yes, the complexity is order of 1. Means we had started from linear search whose complexity was order of n. We came to binary search whose complexity was order of log n with one constraint that the list should be sorted one. Next we moved to binary search tree in which the searching time complexity was order of log n, but still it was not guaranteed. It can go to order of n. when the tree is skewed. Then for a guaranteed order of log n, what did we do? We balanced that BST, and that was said to be AVL tree. Now we tried to improvise the solution, and we have improved it in this fashion that elements are stored in an array at its own index value. So we found the complexity of searching in this case as order of 1. But is it very much efficient? Let's see with the help of one more example. Suppose we are having the elements as 8, 3, 13, 6, 4, 10, which we had taken previously, and we have included one more element as 50. Now what happens in this case? So we are just creating an array of size 50, and we are storing the elements at its own index value. So 8 will be stored at a location 8, index value 8. 3 will be stored at the index location 3. Similarly, 50 will be stored at the index location 50. Now we want to search an element. Suppose we want to search 10. So yeah, we can search 10 directly by going to its index value. So yes, we can search it in order of 1 because directly we can go to the index value 10 and it will search in order of 1, that is constant time complexity is there for searching an element 10. Similarly, if we want to search another element as for example 12. So in this case, we can again search that element 12 in the list by directly going to the index value 12. So it is again done in order of 1, means constant time complexity. But it has a great disadvantage. The disadvantage is that in order to search 50, we can go to the 50th location. That is not at all a problem. But the problem is that we have increased one element here 50, and we had to increase the space of the array from 14th index till 49, which is wasted, which is not at all used. So it has a great disadvantage that a lot of unused spaces are created in the array, which we are not going to use. As for example, I repeat it, it's very important point that we had increased one element in the list and that element was 50, and when we increase one element, that we have seen here that we had to increase this space from 14th index to 49, which is left unused. We have not used it. So what does it refer to? It refers to the fact that we have enhanced our time complexity in order of 1, but again we failed to save the space. So space complexity has increased, so we cannot say that it is one of the very good algorithms to deal with this kind of searching. Next is that is there any some other way by which we can do this? Do this means we can search an element in order of 1 and at the same time we can save this space also. So yes, we have. And what that technique is called? That technique is hashing. Means hashing is a technique which will help us improve the time complexity and improve the space complexity also. As we have seen in our last example that we had improved the time complexity to order of 1, but we could not work very well with the space complexity. We had wasted a lot of space. So coming to hashing, what hashing is? Hashing is a technique of mapping the elements values to a hash table with the help of a hash function. We do have some elements key 1, key 2, key 3, which were the elements we had recalled in our last example of array. So here we have key 1, key 2 and key 3, and these key 1, key 2 and key 3 are mapped to a hash table, but they are mapped to a hash table with the help of a hash function. Means hash function will be responsible to map these elements to this table, and this table is said to be the hash table. Okay, so we will understand it with the help of an example. I repeat this, these are the elements which are supposed to be stored in a hash table, and that storing of these elements in the hash table will be done through a mathematical function, and that function is said to be the hash function. Now, suppose we want to search an element key to, then we will search the element here. We have a mechanism for searching that we will see. Suppose we have taken example where the hash function is hx is equal to x, where x is the element which we want to search, or the x is the element which we want to store. Better call it x is an element which we want to store, and hx is the hash. So suppose these are the elements. The same example I am taking, which example we had dealt in the case of array. The elements are same. So the elements are 8, 3, 13, 6, 4 and 10. Now we want to store these elements in a hash table. The definition of hashing says the same, that elements of a list should be stored in a hash table with the help of a hash function. So we need three things to store the element. The first one is element itself, that we have here as 8, 3, 13, 6, 4, 10. The next is the hash function, which is given here as hx is equal to x, and the next one is hash table. So this is hash table, and the index value runs from 0 to 13. Now we are mapping 8, this element, to this hash table. Now where this element 8 will be mapped to the hash table will be decided by this hash function, right? So 8 is mapped to 8. Why? Because the element, the hash of 8 is equal to 8 itself. I mean to say, means 8th is the location, hash location for this element 8. That's why 8 is mapped to an index value 8. Similarly, 3 is mapped to 3, 13 is mapped to 13, 6 is mapped to 6, 4 is mapped to 4 and 10 is mapped to 10. But then we can understand that this example, this mechanism is same as what we have dealt in our previous example of array. But still we can call it hashing. We call it hashing. What is the reason? The reason is that we have introduced a hash function. In case of array, the hash function was not defined. But here we have defined a hash function as hx is equal to x. So that's why this is an example of hashing. Okay, so the access time is order of 1, but it is same as storing the elements in an array that we have seen in our last example. Then what is the use again? Yeah, we can change the hash function. We can change the hash function according to our own convenience, so that minimum of the space are left unused. The algorithms become efficient. That's why we are in a condition to modify this hash function. We will always have that flexibility to modify the hash function. Okay, so let's modify the hash function. So now the hash function is x mod size of the hash table. So elements are 8, 3, 13, 6, 4, 10, the same elements. And suppose we are taking a hash table of size 10, means index runs from 0 to 9. Now, in order to store 8, what is the hash value of 8? H of 8 is equal to 8 mod 10, because the size of the hash table is 10. So 8 mod 10 is 8. So the element 8 is mapped to the index value 8. Similarly, the next element 3 will be mapped to 3 mod 10 index value, and that is 3. Next 13 mod 10 is again 3. So 13 will also be mapped to the same index location 3. 6 mod 10 is 6, 4 mod 10 is 4 and 10 mod 10 is 0. So in this way, all the elements in this list are mapped to the hash table based on this hash function. Now, the search time has improved as order of 1. How search time has improved? Let's see. Suppose we want to search an element 8. Then we will directly search 8 at index value 8 mod 10. So yeah, 8 mod 10 goes to index value 8. 8 will be searched at index value 8. Similarly, if we want to search 10, so we will search 10 at the index value 10 mod 10. 10 mod 10 is 0. So we will look for an index value at 0 and we will find 10 here. It means that we did not traverse the total hash table, but we found the element which we wanted to search in constant time in order of 1. Here one issue comes into the picture. As we can see here, the two different elements 3 and 13 try to occupy the same slot, and that same slot is 3 as we can see here. So when it happens, then it is called as collision. In our next video, we will be discussing about the collisions, different kind of collisions, and the algorithms to resolve collision with the help of some more example. Thank you.